It will be helpful to show the shape of one instance after transformation. We have this maybe input, and it has been through the K transformation, Q transformation, and V transformation. Maybe we swap them. Let this be Q and this be V. Okay, and then it becomes this number M is 50 for now number, and this 512 dimensions. This represents the information, one form of the information from this input, and we want this is K. We use this form as a query, use this form as K, and let each part of the input data to try to look at other parts of the data and calculate the relationship. It will be as we have a sequence of one part, two part, three part, four parts, 50 parts, and with the same guy, we have 50. Okay, and we want to form an attention, so-called attention matrix, and at some entry of this attention, that will represent the token at this position is relationship with the token at this location. Okay, let us call this we call these two parts query and K. Okay, so what we do if we are going to compute the inner product, we keep the query matrix this way, M, and this dimension represent this dimension represent the information vector for query, and we let the K transpose. So this K transpose. So this is the information vector dimension, and this consists of M instances, and we do the matrix multiplication. We will have an M by M attention matrix. This M by M attention matrix represent for this query its relationship with the existing case, and we link the case to the values using the language of database maybe. So we use this weight to combine to this value, this weight to combine to this value, so on and so forth. We do another matrix multiplication. Then that's it. So when it comes to coding, here is what we do. So we need to use the XQ. The matrix multiplication is represented in this way in PyTorch, and xk dot, we need to transpose the xk, but we don't want to touch the first dimension of which would represent different documents, and it's largely independent to the computation discussed here. We only consider these two dimensions in the previous discussion. So transpose the last two dimensions, -2, -1. Okay, so let's call that A, and see the shape of this. Fine, 50 by 50. Okay, and let's see, call that out. So look, it becomes 4 by 50 by the the desired size of the output vector. Of course, for example, you can change the output size of the vector. This is possible, such as, let's call that 96. If you do this, okay, but we have to come, because of the requirement of the matrix multiplication, we have to keep the inner dimension of the k and the query the same. But we can change it as well if we want. Okay, everything works. But usually we just keep the same dimension over here. Okay. So that's the core mechanism of computing the attention. But of course, there are a lot of layers to build around this core. For example, the first one, we do not just use this combination sort. We need another layer of which is called output transform. So this will get a linear out, and then the true out will be out. Okay, there's more complexity building this way. We will discuss in later videos. But the first one, we do an important change, important improvement on the attention mechanism itself. So instead of computing one attention score between two locations, we compute multiple. We compute multiple by cutting those attention information. We call that the attention information matrix. Maybe that is a misnomer, but you get the point. We cut it into different parts. For each part, we call that a head. A head. It's called attention head. We will build a multi-head attention mechanism in the next part.